Today, the essential question is, how can we measure the water potential in a living cell? The skills that we are going to practice is representing and describing data, construct a graph, as well as statistical tests and data analysis, perform mathematical calculation. Within that, we will focus on the percent change calculation. Last class, we modeled the diffusion and osmosis with artificial membrane. Recall what you observed. Write one observation on your whiteboard and leave the whiteboard on your table. Now stand up, walk around the classroom, get your 2 sticky notes from the bin and a pencil, and leave comments on 2 of the whiteboards on your sticky notes. When you're done, go back to your table and sit down and wait for another instruction. So what did you learn from the gallery walk?
Depending on the different concentrations between 2 compartments, water or smaller particles can pass through the dialysis tubing.
So what small particles do you refer to in your answer?
Ions and glucose were able to pass through the artificial membrane.
Very well said. Now let's discover how living cells behave if they are surrounded in hypertonic solution. First, get the container from on your table. The container contains a glass slide and 2 solutions, 0.9 saline solution and 2.5% saline solution. You will take out the outer skin of the onion, place it on the glass, and put 0.9% saline solution on the onion skin. Put it under the microscope on the stage and use first the 40 magnification, zoom it and turn into 100 magnification to check how the cell looks like. When you see the cells, take a picture with your cell phone and post that picture on your OneNote page. Clear? Any questions? Now let's start to work. Now at your table, you have another bottle that contains 2.5% salt solution. Definitely this is hypertonic compared to the 0.9% salt solution. You take out the slide again with the onion skin on it, add 2 or 3 drops of 2.5 saline solution to the onion skin and check again under the microscope what happens to the cells. You can check it first with 40 magnification, you turn the objective into 100 and magnification and 400 if you are good enough on that to check the cells. After that, would you please take a picture again with your cell phone and post it in your OneNote page. Let's start to work. Can somebody share her OneNote page with the 2 pictures and we can compare the 2 pictures that you took under the microscope? Rosha, can you just share your picture? Okay, it's on the overhead. Thank you. So what can we notice between the 2 pictures? how did the cell behave the first time and when we added the hypertonic solution, the 2.5 saline solution?
There are big white gaps between the cells now on this second picture. I assume that this means the cell lost water because the surrounding was hypertonic, and we learned that water moves from hypertonic to hypotonic solution.
You just say
It's from hypotonic to hypertonic solutions.
Good.
You can just cut them.
So the two pictures, can you predict what would happen to the mass of the cells in here when we add hypertonic solution around the cells?
The mass of the onion skin tissue would decrease.
And what would happen to the mass of the cell if the outside is isotonic compared to the cell of the onion?
The cells would not shrivel up and there would be no change in mass.
This is a very good thinking, and this is what we are going to use in our student-driven investigation to figure out the molarities of the different solutions that you will see on the table, as well as figuring out the water potential of the vegetable or the fruit that you will get or you choose. So on your table you see 6 test tubes, and the 6 test tubes have different colors in it. One of them contains 0 molarity sucrose solution. That means there's no sucrose in the solution. Another one is 0 molar, 0.2 molar solution. The other one is 0.4 molar. The next one is 0.6, 0.8 molar sucrose solution, and 1.0 molar solution. You do not know what color belongs to which sucrose solution. Here are some materials that you are going to check for water potential. This is rutabaga that I bought from the store. Sweet potato, another choice. Potato is another choice, as well as the squash. Recall together now what contributes to water potential with the help of your formula sheet from the AP biology equations and formula sheet. So, anybody? We'll have water potential 5, and I put here is water potential equals
The pressure potential.
The solid potential.
water potential equals to pressure potential plus the solute potential. For us, let's do the calculation for the water for the solution that is 0.4 molar. And because we are using open container in the test tube, it's not sealed, so the pressure potential is going to be 0. Water potential 0.4 molar solution is 0 plus minus 1 times ICRT. This is, I'm getting it from the formula sheet, from the AP biology equation sheet. Let's plug the numbers in. 0 bar plus minus 1 times the I is the ionization constant. For sucrose is 1. For sodium chloride, if we would use salt solution, it would be 2, because the salt dissociates into its ions, the sodium and the chloride. But in our case, the sucrose is having one ionization constant. The unit is mole per liter. The R is the pressure constant, that is 0.0831. The unit is liter times bar over mole times Kelvin, and we time that with the temperature. The temperature is in Kelvin, please recall it, and we are dealing with 20 Celsius room temperature, so 273 Kelvin plus 20 is going to give us 293 Kelvin. 293 Kelvin. Can I ask somebody to plug? Before that, let's simplify. Liter out, mole out, Kelvin out. So pretty much we will use, we will use bar. That's what the remaining is. Can I ask somebody to just figure it out? Please use your calculator.
Negative 9.7 bars.
So for the water potential, what you said is negative 9.7 bars. I'm so glad you added a negative sign. Let's calculate on your own now the water potential for the solution. That is 0.6 molar sucrose. Everybody is working on their own.
We have negative 14.6 bars.
I put it in here 0.4 molar, and this is 0.6 molar. What is that going to be? Thank you, 14.6, that's what you said, bars. What can you notice between the tonicity and the water potential? Yes?
As the tonicity increases, the value of the water potential decreases.
So in that case, we can say that the water moves from a higher water potential to a lower water potential.
Exactly. That's totally right. That's what we are going to use to find out the water potential of the rutabaga, or the potato, or the sweet potato, or the squash's cells, the water potential in them. Any questions? Let's start to work. Give me just a couple of seconds that I will just do some administration stuff, and I will just walk around in the classroom and answer your questions if you are stuck. Let's start to work.